Okay. So today what we said is to find the reflection coefficient, we use this formula. And remind me what the question is in the homework, if you can.
The question is, assume that ZL equals 100 ohms and calculate the reflection coefficient of gamma L at Z0, where gamma L equals gamma L over A.
Let me see. Like, could you let me? I need to find it. Could you just then share? Do you have it available there so I can see it?
Yeah.
Okay. Let me. I will stop sharing here. So could you share it with me? Just so I need to remember it because I don't have it here available. And then I can address that specific question. Ah, let me see. Can you increase it a little bit? Ah, okay. It says, okay, so it gives you a ZL, which is 100 ohms, and calculate the reflection coefficient at Z equals 0, okay? And at Z equals D, obviously, yeah. Okay, so this is the expression we're using for the reflection coefficient. So practically, so let me go to then a different place here, and I will share my screen now. I just saw it, okay.
All right, then let me stop sharing.
Yeah, thank you. So, all right, and let me share it, share screen. Okay, so I'll solve a similar problem, but different, not exactly that. So let's assume that I have here a transmission line, and I will do it a little thick here, line, all right, here. And then, so this is A prime. And then I give you this to be ZS. And then this one. And then here the load. So here's B prime, and then the load here. And let me assume that I give you this to be whatever. I give you this to be 30 ohms, for example. I give you Z naught here to be 50 ohms. I give you frequency to be 10 gigahertz. And I know that in free space, the wavelength is 3 centimeters. And then I give you this, for example, D to be 10 centimeters or 12 centimeters. Okay? And then I want you to find the reflection coefficient here. That's how, well, excuse me. How I show the reflection coefficient is like this. All right, so I want, so this is a visual way of showing. I want to find gamma L, gamma at A prime, first of all, and then I want the reflection coefficient here, which is gamma at B prime, and sometimes at the load, or many times, I indicate gamma B prime as gamma L. Okay, what are the formulas that we have that I was using before, which you need to remember? That gamma at any point Z, let's assume this is any point Z here, all right? This is point Z, meaning this is Z, and this is Z prime, which is one is from the source, your distance, the other is from the load. Okay, so I have gamma of Z, gamma at AA prime, gamma at any, let me call this, first of all, give you the general formula. Gamma at CC prime is Z input. That's the definition. Oh, well, no, the definition is not that. Let me start with the definition just to remember. It's V reflected at Z divided by B incident at Z. But what we found is at that point, this is Z input at Z minus Z naught, Z input at Z plus Z naught. Okay, so the deflection coefficient at the end, gamma at B prime, therefore it's going to be ZL. That's the input impedance at BB prime is exactly your load. ZL minus Z naught, ZL plus Z naught. So that is going to make it what? 30 minus 50 over 30 plus 50, which is minus 20 divided by 80, which is minus 0.25. All right? And then it asks, that's one, to gamma at A prime. So I will have to find Z input at A prime, and then use the formula, minus Z naught, Z input at A prime plus Z naught. All right, how much is your Z input at A prime? According to the formula we found is Z naught, ZL, let me write it here, plus J Z naught tangent of beta Z prime over Z naught plus J ZL tangent beta Z prime. All right? So at Z equals 0, at that point, Z prime equals D, which is the distance. All right? So we have that Z input at A prime equals Z naught ZL plus J Z naught tangent of beta D Z naught plus J ZL tangent of beta D. How much is beta D? Is 2 pi lambda times D. So it's going to be 2 pi, what? 2 pi 12 divided by 3, which is 4, 8 pi. All right, how much is the tangent of 8 pi? What do you think?
My calculator is saying it's basically zero.
Exactly, it's 0. So practically for this case, this is 0, this is 0, and therefore this is ZL. So it happens for that length of the line, your Z input at AA prime to be ZL, which is 30 ohms. So your gamma AA prime is going to be similar to your gamma at the end of the line. All right, so it's going to be minus, for this case, to 5. It just happened. Now, is that helping you with your with the homework, or is it something else that confuses you there?
So basically, gamma L is basically just the reflective coefficient at the end
Mm-hmm.
of z of
Exactly.
0.
Mm-hmm. Yes,
Yeah,
exactly.
thanks. That helps a lot.
Okay, yeah. Any other question in relation to the homework?
Just wanted to check with the, I just wanted to look at the equations again. So,
Which
okay, so
equation? These ones or some other ones?
yeah, these ones like
Yeah.
1 and 2. So let's see, for RB, you had CL minus C naught. And so so B says
Where are you now?
like the first one. So
Here.
RBB. So that's the,
There's not R, that's
or sorry,
gamma.
gamma. Looks like
Yeah.
an R to me. So I just instinctively say
I'm
that.
sorry. Yeah. No, it's gamma. That's my way of writing gamma. Yeah.
Okay, so the gamma is gamma BB. So okay, so ZL minus C naught. So
Z naught, yeah.
so ZL. So it says it's 30 there, and then the Z naught was that given to us? Okay.
Yes.
Z naught
Yeah,
is 50.
yeah.
Okay, and that's how you got that.
Yeah.
And then the gamma CC. So that's just like a arbitrary
Yes. In the
value.
mid. Yes. It's more of a general expression rather.
Okay. And then for the second case, you have to
Down here, you mean?
try to actually solve for
Yeah.
Zn.
Yes.
Okay.
I can
so
solve. Yeah.
So for RBB, so
Gamma.
the input, I'm really sorry. I just keep
No,
messing
that's,
up.
don't ever apologize. I will just correct you until you say gamma because. Yeah.
Okay, so
Okay.
okay, so the input impedance is equal to the load impedance. So just thinking about that conceptually. So
This one. You're referring to that?
gamma BB. I mean,
gamma BB here.
So okay, so the load impedance is the input impedance in that specific case. I think I forgot, like what exactly the.
So the general expression is this, but for gamma at BB prime, you're right at the load. So the impedance you have there is the load impedance. See, so for example, here you have Z input at B prime to BZL, because that's what you see. All right, so for example, if I were to, for a moment, take this out, if you stay at BB prime, you're sitting there observing the load, what you see is just the load, all right?
Okay, so input impedance is just what you're observing from your perspective.
Yes, exactly.
Okay.
Yeah. So you always see the arrow. The input impedance, it always looking towards the load. Everything is going towards the load. You see that? Always. It's like you're facing the load all the time. Even the reflection coefficient, you are facing the load always. Here, for example. That shows reflection, the little arrow like coming back. But you always face the load. What else does the homework say? What is it asking you?
It's also asking for us to find the phase of the impedance as well.
Okay. And how much is it giving you? So practically the impedance is going to be a complex number. Obviously, all right. And then which phase? The phase where the impedance at the source, like in the beginning of the line, looking towards the load. Is that what?
No, it's saying as a function of z.
Let me see. So could you share it again? So I can see. Assume that ZS is 50 ohms. The source is resistive. What value of length D and what value of the characteristic impedance Z naught will make the reflection coefficient gamma L at AA prime equal to 0? Okay. And find the input impedance at Z input and A. Okay, we got that. For the same, says 2, for the same value of ZL, find the phase as a function of Z and confirm with your values. Okay, let's do 2. You want to do something similar to 2 here? All right, so let's, what we are going to do, take this one and move it, copy it, and place it here, paste. Okay, so now if we say here, this is example 1, say 1. Or A, B. Again, B, find the phase of gamma at C prime. Remember this, let me use a different color for C. No, did not take that. C prime, right? So the reflection coefficient at gamma C prime, and is for any position, is going to be equal.
Professor, you're not sharing your screen.
I'm sorry. Okay. Okay. So what I did is that I moved down. We are the same next page. And I have the same problem, and I'm asking now to look at the deflection coefficient at C prime, the reflection coefficient when you are there, and then find the phase. And then confirm with the general expression with the values at BB prime, which I found before, and an AA prime. So in that position at Z, we said it's going to be Z input at Z minus Z naught, Z input at that position. So practically, see, instead of Z, what I'm going to put here, C prime. That's how we saw it, C prime, minus C naught, plus C naught. Okay, so that is the expression. Let us try to find Z input at C prime, which is Z naught. And here we have ZL plus J Z naught tangent of beta Z prime according to our formula. Z prime is this one up there. Z naught plus J ZL tangent of beta Z prime. Okay, now there is a formula in also the book which I can derive, and I will derive it for you, but is in also the book. And let me tell you in what page. It's chapter 11. Okay, that image. Yes. Okay, it's on the book. It's page 567. So on book, chapter 11.4, page 567. Practically is equation 1137. There, you're going to find the following important relationship. You're going to have that gamma at CC prime is equal to gamma at L or BB prime, all right? So let's say the gamma at the load times E to the minus J to beta. Let me see what L is prime. Yes, okay, so it's like our Z prime. The book has it as L prime, as a matter of fact. We have it as Z prime, all right? So the book has it L prime. Okay, so that's what you find out, where your Z prime is that distance, all right? Z and Z prime are related, obviously. You need to remember Z plus Z prime is nothing else but D. So if you know one, you know the other, okay? And Z and gamma at B prime is gamma at L, which we found to be minus 0 to 5. All right? So practically gamma C prime from here is equal to minus 0.25 e to minus j to beta z prime. And there is a minus there. So when you write it as when you write it, this one as a complex number with a magnitude and a phase, you have to remove the sign, obviously, all right? So how do you write minus 0.25 as a complex number with a magnitude and a phase? Do you know how you write it? 0 to 5 and an exponential, what? Of minus j. What is going to give you a negative sign as an exponential? What is good? Minus what?
Minus pi, I think.
Minus what?
Minus pi or
Yes,
180
exactly.
degrees.
Minus 180. Perfect. Or minus pi. Exactly. So you're correct. So this is equal to 0.25 e to the minus j pi. All right. So what I can do here is to take these two, go here, and what do I have? That gamma C prime is going to be 0.25. Let me also move it a little bit. And then I will have E to the minus J pi plus 2 beta Z prime. All right? So that's how I can write it. From there, I can find the reflection coefficient at any point. So from here, let me call that, instead of having that, because I'm going to change, when I make that into a, let me write it here. So, because when I make it into notes, it's going to split on the page. So I want to be careful because people will get confused. Okay, so we found here that this is equal to point. That's the magnitude to 5. And the phase is pi plus 2 pi 2 beta z prime. Now, let's check it out. At the load, what do we have? Z prime equals 0 when we are at the load. You remember? Look at this. If I move from here, I move to the load, my Z prime becomes 0. Do you agree?
Yes,
Okay, perfect. So at the load, that is true. So then what do I have? Gamma CC prime equals 0.25 e to the minus j p, which is exactly what we got before, which is minus 0.25. Okay? And at the source, what do I have? Gamma A prime to be 0.25 e minus j pi. And how much is z prime at the source? Z prime then becomes, now I move on the other side. So from there, I go here. So my z prime becomes d, all right, when I got the source. And therefore, I have here plus 2 beta d, which means is 0.25 e minus j, and then I have pi plus 2 pi over lambda times d, which is 0.25 e to the minus j pi, and then as I had it minus j, and then is 8, I believe 12 for 8 pi. All right? So that's going to give me exactly what I found before, 0.25, which is there. All right? So that's how we do this. That's how we solve that part of the problem. All right? Then, then it has another one, another piece which is important. Then it asks you to find, then just read it to me, the last question.
The last question is, assume that ZS equals 50 ohms is resistive. What value of length D and what value of characteristic impedance Z0 will make the reflection coefficients gamma L divided by A prime equal to 0?
Okay, so this is C. Let me then do this again, take it one down. So let me do this. Okay, now what is asking me, let me erase some things there. I assume this is not Z naught because it's asking me, all right, you remember? And then it's asking me about the length too. Let me, I will keep that D. Okay, D. And I will erase the in between, just to make things simpler. I will erase that for now. This, since we're on the other end. This. And what I want to do is at A prime. So then is asking me to find Z naught and D. So gamma, find, therefore let me write it here, what we are going to find. Find Z naught and D, so that gamma at A prime equals 0, we said. What is gamma at A prime? Now let's think about that. When you are at A prime, what you see in front of you when you look towards this direction, let me erase the gamma for a moment, and then I will place it again. When I'm sitting right here, okay? And then I'm looking this way. What I see is an input impedance here, Z input at A prime. That means that as I am here on the side of the source, what I see, so this part of my circuit, this one, is gonna look like that, like here. It's gonna look like a source, then ZS, then here what is the equivalent?
Z in.
Exactly. So practically, I have this simple circuit. V naught here, ZS, and Z input. And is asking me to find the reflection coefficient here. Here. So practically, what I will do, I will apply exactly the same formula for the reflection coefficient. But instead of a characteristic impedance, I will have ZS. So because the characteristic impedance is gone, I don't see a line anymore. I see Z input. So practically, what I will have is that gamma at A prime now is going to be at what I see here. Z in, well, let me see. It says, does it say the reflection coefficient, or what does it say? What else does it say? It says the reflection coefficient to go to 0, or it says the input impedance to become 50 ohms.
It just says to assume that the ZS is equal to 50 ohms is resistive.
Okay. Yes.
And it's asking us to determine the length D and impedance Z
Not.
0.
Yes. So what does it say? Read the rest of me. The expression I want to hear.
We'll make the reflection coefficient
Okay.
gamma.
0. Yes. At that point. So when we get rid of the transmission line, what we are using as a reflection coefficient anymore is this relationship. Because we don't see a transmission line anymore to put Z naught, all right? That's all that we see. This is not indirectly in circuits, you have seen that. And you have seen that when we talk about matching in circuits for power. You remember conjugate matching or matching in circuits for power? When you match something to a source, or the conjugate matching, you remember that a little bit? Did you do that in circuits?
I don't think so.
Okay, maybe you did it and then you did not talk too much about it. Or maybe the faculty who covered it did not cover it. That's possible. Okay, that's all right. That we are gonna remember it again. But in any case, pardon me?
Sorry, is the ZIN on the numerator not the same as the one on the denominator?
It's the same.
Okay.
Yeah, sorry. Let me move that a little bit. Yeah, it's the same. So in any case, when the line is gone and we have only the input impedance there, which we know, and then we only have the source behind it, then in that case, the expression for the reflection coefficient is this one. And we do that because we want to match to the source anymore. All right, as we say, we want then to have the maximum power transfer of power from the source, which has an internal impedance Z sub S, to the load. But in any case, you're going to remember that. You're going to remember now that the moment you replaced your line with an input impedance like we did here, then your reflection coefficient in that circuit has this form. It then expresses itself in terms of the input impedance there and the impedance behind you, which is ZS. But ZS, we said, is 50 ohms. So now we want to make sure that this one is 0. To make this one is 0, it implies that Z input at A prime has to be ZS. That means has to be 50 ohms. That's what we want to do. Okay? What is the expression for that input impedance from previous? That was given by this expression where Z prime equals D. So let me now write it again. So Z input at AA prime equals Z naught ZL, which is given, plus J Z naught tangent of beta D and Z naught plus J CL tangent of beta D. We want that to be 50 ohms. All right? Keep that in mind. We want that to become real. Now, we know ZL that has been given to us. It was like 30. That is not going to change. So from here, we know that Z naught, which is unknown, times 30 plus J Z naught tangent beta D, and D is unknown, divided by Z naught plus J 30 tangent beta D is to be equal to 50. So now I multiply both sides with the denominator. So I have Z naught 30 plus J Z naught tangent of beta D has to become equal to 50 Z naught plus J 30 tangent beta D. All right, so then I separate the real parts and the imaginary parts, and I have Z naught times 30 has to be 50 times Z naught, all right? And, which is not possible, obviously, but let's see, we'll understand why that we'll see what we're going to get. And then the next, so if we, let me put it down, and then the exponential part will be Z naught square J tangent beta D to be equal J 30 times 50 tangent of beta d. Now, so obviously that cannot apply, all right? That's not possible for any other values but the ones where tangent of beta d becomes infinite. Why is that? So that not possible. Let me write here. Not possible unless tangent of beta d is infinite. Now, the reason it is in your homework is because I'm gonna cover something on Friday that is gonna make it much easier, but now we are gonna derive it, obviously. After Friday, you did not have to derive it. But in any case, so you see, this one may only be possible, so let me put here. So only possible if z naught tangent beta d much larger than 30, all right, and 30 tangent of beta d much larger than z naught, which means that if my tangent of beta z becomes infinite, beta d, then that applies. Do you agree?
I guess since can't you split up the tangent into a sine and cosine and
Yeah,
then multiply
you're
the
gonna see.
cosine?
Yeah, you don't even have to do that, because if you assume this is true, then you go back to this formula and then you assume this is so small that you ignore it. You assume that this is so small that you ignore it. And then that formula becomes the following. So under these conditions, this one here becomes what? Then it changes. I'll use red to see. Z naught, and then I will write it. J Z naught tangent of beta d over J30 tangent of beta d equals 50. This one goes, this one goes. So what I have from here is z naught squared equals 30 times 50. And from here, I have that z naught is the square root of 30 times 50 that I found there for z naught. And then from here, from this one, not on this one. From this one, I go down here, and what do I find? When does tangent beta d become? When does it become infinite? When the cosine goes to 0. You agree with that statement?
Yeah.
Okay, so beta d is infinite. That means beta d has to well, the cosine, let me write that first. Cosine of beta d has to become 0, which implies what? Beta d has to be either pi over 2, 3 pi over 2, 5 pi over 2, okay? And so on. Let's look at the smallest one. When beta d becomes pi over 2, that means 2 pi over lambda d has to be pi over 2, which then it means that D has to be a quarter of a lambda. So that is something extremely interesting. When D becomes a quarter of a lambda, then practically what it tells me is that, and when D becomes a quarter of a lambda and Z naught becomes the square root of the load times of the impedance I want to see, then practically I can match it to 50 ohms or any other real impedance. Now, why is that important? Look at the following. If you have a load here, which is 30 ohms, or anything, as a matter of fact, could be 30 for this now, and then I put a section of a line here, which is a quarter of a wavelength, lambda over 4, then I can select my Z naught. This is quarter of a wavelength, right? Let me put it there. I can select Z naught to practically get here any real input impedance. In that case, we wanted this to be 50 ohms. So let's call that ZS because we wanted to match to a load. There was here, ZS. So a quarter of a wavelength line, and then let's assume that this is ZL. A quarter of a wavelength line that has a real load and wants to match to a real source impedance, practically it can do that if the characteristic impedance of the line is the square root of the load times the source impedance. And that is a very important section of a line and is called the quarter wavelength transformer. And you will always remember it, transformer. We'll cover it. We'll do it as an example, like here. Oops. Why? It is not right. What is it? Oh. First time it's not writing. Why? Ah, okay. Transformer. Sorry, it was like the pen. The pen what had been. All right, so that is an important transmission section of a line. It's called the quarter wavelength transformer because it is a quarter wavelength and because it can match any real load to any real source impedance. So that is how we found it. But this one, after you prove it, you just use it from that point on. You always remember this formula and you use it. Okay, and so that's how you're going to do that. Okay, any questions about this?
Can you go back up to the original part of the question? I just don't think I remember exactly what we were solving for here.
So we try to find Z naught and D. So the reflection coefficient at the front, this one is equal to 0, which means, in other words, the input impedance, Z input at AA prime is equal to ZS.
Wait, didn't we cover something like that today?
Not
remember
exactly, but similar. Yes. I mean,
Um,
they're all the same. You know, I have to tell you, in all of these examples, you will see the same things over and over again. It's just that there some problems will ask this question, some other problem will ask a similar question, articulated a little differently, but they are all very similar. So you see the same equations rather.
Because I just remember there's a case where
Yes, they're the small ones, isn't it? Yeah, for another reason, we did exactly the same. Yeah, in the problem today, in the theory. Yeah, but we did not solve exactly this, however. But we did exactly the same thing up here. We also played with this. I mean, considered that, you know, if it was in the open end, it was like when the load is infinite. That's what we did in that example. But that's how you're going to do this. Or you can use it directly, but since if you're gonna, after Friday, you can just say this is a quarter wavelength transformer, but you can write this down, similar kind of approach. You can follow up in the other problem that I gave. Okay, that is. So what other problems do you want me to solve? Do you want me to do another problem? Let me see, what else would I do? We can do different problems. Are you ready to do one more? I don't hear anything. Are you guys listening? I don't even know whether you're listening.
I don't think I really have anything in mind right now.
Okay. Anybody else?
Yeah, I don't have anything else in mind either.
Okay. Any questions then with this in relation to what we covered so far that you want me to go over again? All right. If not, then what I will do is that I will clean these notes and I will upload them together with the recording. So you can go over them again if you want. And for others too. All right. So that's what I will do. So I guess if we don't have anything else, any questions, then probably we're gonna just take off. Unless somebody has an additional question.
I have a small question on,
Sure. Yeah.
I think it was part B, when we were solving that part, or when we had to find the reflection coefficient for like AA prime.
Yes.
So like, okay, like you solved for beta or beta D at one point, and you got like 8 pi.
Right here.
Wait, hold
Here,
on.
here. We got it here. It was, let me see. No, we got that here. 8 pi here. That's what you mean. Yes.
Yeah, like when you substituted, like, 'cause I think somewhere earlier we had solved for, yeah,
Yes,
beta D, and it was 8
yes.
pi.
Yes,
Yeah.
we had also, yeah, here.
So then, like at the bottom, because down there was 2 beta pi, so would this be 16 pi or would it be 8 pi? Because like when
I
we were
was
doing,
I was 2. Yes, it was 16. Thank you.
okay,
Would have been 16, but the result is the same because either 8 or 16 pi will give that to be 1. But you are correct.
okay.
It was excellent. Yeah, 16. Yeah, let me do it in blue. Yep, thank you.
Yeah, no problem. Thank you, Professor.
Absolutely. Thank you. All right. Let me see. So we'll see you then on Friday. Okay, take care.
You too. Bye-bye.
Bye-bye.